Gabriel? Okay. So the speaker is Gabriel Ebner from Microsoft Research.
Okay, does this work? Okay, well then let's try it. Okay, so we're already a bit over time, so I'll try to stick to the important parts. So first of all, thank you all for having me. This talk is at the end of the day. It's already, the afternoon is already a bit over, and this talk is more about like F star. So so I want to tell you about our work on doing like machine learning and LM generated verification in F star. It's going to be similar to Dafny' in the sense that it's SMT verified. And I'll try hard to point out learnings from this that are more broadly applicable to other languages like Dafny'. So let's get right into it. So in a sense, F star looks a bit like Lean or Cog or Dafny' in the sense that like you've got code. It has types, and like whenever you need some verification conditions in your code, it gets sent to C3. However, F star is a bit more syntactically difficult than Dafny', and I've just put on a small example of F star on the slides, which is a quicksort function. It's defined recursively as a functional program, and it's defined using recursion. It calls to some lemmers, I guess, just as you would do in a Dafny' program. And the task that we have been investigating and trying to see how well do models on that task is the simple task where we give the model like a description of the problem in the form of like the name of the function and its type, and ask the model to generate the whole definition and see how well they do on that. Okay, so for that task, we've done two big things. One is to gather a data set of F star code of like verified program code in this SMT-assisted proof-oriented programming language, and then we've trained models on it and evaluated them. So let's first get to the data set. So I guess like the big difference here is that we've been trying to gather like every single F star code, F star project that we could get our hands on that is on GitHub. That, papers that were written 5 years ago, we tried to port it to the current F star version. And in total, we get about 1 million lines of code. So we're not just focusing on like standalone files. We're making an actual effort to learn from code that is like in the middle of some repository. And we're trying also like I was trying to learn from stuff that's in the middle of a file, and so we can really make use of like the whole code base that is out there, and this spans like a lot of different topics. I mean, some of it is like something that you would reasonably expect an LLM to generate. Some easy lemmers about lists, some easy like recursive functions, sorting functions, and then it also contains stuff like verified crypto implementations. And various distributed algorithms and separation logics. And, well, you just put everything in there, and then you see how well it works. So one complication that we have in F star that might or might not be that visible in Dafny' is that a lot of things in F star, just like as they are in Cog or Lean, are syntactically the same. If you have a type, if you have a proposition, if you have a lemma, if you have a program, they are all just first-class values in your language. And syntactically, they look very similar, almost the same, which is great because you can have a list of types, you can have a list of proofs, you can have a list of propositions, you can have a list of programs, and they all work the same. But for our evaluation purposes, we needed to classify those definitions because, well, we expect the LLMs to do differently depending on whether they try to synthesize like some type or whether they want to synthesize a fully specified program. So I've given you some like stereotypical examples here in F-star syntax, right? So you can define refinement types, and those are like just first-class values, and they look the same as a simply typed function that just takes two natural numbers, gives you another one, and does not have any other specification. It could return 0. It could return 42 with a comment as a smiley, or it could add them. Like you cannot tell from the type, and so the task that we're evaluating on, generating a type-correct definition, is going to be relatively easy. And then you can also have like theorems that are also introduced syntactically in the same form, and where you might these theorems, they can be arbitrarily hard, and in particular, like for these theorems, it does not matter what the model generates as long as it checks in F-star. It's good, and we are accepting the output. And the same goes for intrinsically typed functions and programs, where the precondition and postconditions already constrain the program well enough that we can say that, hey, if the model can generate an implementation that is type correct, then it's probably going to be good. And in total, we get like 3 different classes of interesting definitions here. One is like simply typed programs. Those, I mean, it would be nice if the model can generate them. In practice, it turns out that models still struggle with that. Then there's proofs, where you ask the model to exhibit some proof term that validates a theorem. And then also dependently typed programs, which we kind of assume that they have a good amount of specification on them. This is all a bit heuristic, but we can see clear differences in our evaluation. And in addition to like the the just plain old data set which does nothing, we also include a whole harness to check the proof. So like given such a type definition and a body, it actually like packs up all the stuff of calling the verifier and making sure that there is like no assumes in there, no admits, that it actually like gets the doesn't modify the type of the definition. And there's a nice Python API around it, and we used it for our evaluation. And as another cleanup step in our data set, we filtered out definitions that are super easy to solve, where you don't need to call any external lemmas, where you can just have essentially the empty definition, like even in Dafny', like just curly braces. And if that already verifies without doing anything, then we filtered it out from the data set. So everything's really non-trivial definitions. So to sum up like this, V1 part of the data set, there is various tens of thousands of definitions, and they are somewhat evenly split between simply typed, dependently typed, and proof definitions. And maybe a point to our data set split. So we have a somewhat very interesting data set split. So since we're not considering standalone programs, we are considering like whole developments, we need to take into account the dependency graph of the projects. And our training split actually like respects that split. So the training set is one with that. So if you like look at the dependencies, there's no dependency from the training set to the test set. And then we have also additionally extra hard test sets where we held out whole projects to test them on. So like I don't remember exactly what we excluded, but for example, if we excluded I don't know, me-TLS star and verified implementation of TLS, then we would not fine-tune models on that particular project and only evaluate it there just to prevent any particular contamination. What we did not control for is accidental contamination, so where you have like 2 files that are very similar, like somebody is talking about uint32 and others talking about uint64. This can also lead to some contamination. We did not control for that though. Okay, so much for the data set. Right, we've got lots of data. We've trying to take this whole project developments into account, and we have a dataset split that really respects the dependencies. And from that, we've done evaluation on trying to predict those definition bodies from their types and names. And So there are some key ingredients in how we set up the prompts here. So since we don't just have a single file, but like whole developments, we can't just pass the whole development to the LLM. We need to filter it down. And so there is, we've done various things there. So one is we're using a kind of retrieval augmented generation where we find some related looking definition from the library. And we do that by taking an embedding of the type and the name, so like the whole thing at the top, like the function signature, and then finding functions in the library whose embedding looks similar. And let me just pick the top one. No, not the top one, but as many as fit in our small context window. So this is like an important part about retrieval augmented generation. And then we also add the names of some premises that look plausible and interesting. So the thing is, if you put in like the whole definition in the library, then this takes up a lot of token space, a lot of space in the context window. So you can only get like a limited amount of information there. But if you only pass the name, then the model can still roughly guess what it should do, but it takes up a lot less space. And for that, we trained an actual custom embedding model. Again, trained on a data set. We know, hey, what names are being used in definitions, and we train a model to predict those names via embeddings. And then finally, we add what the model should generate, like kind of the type and the name of the definitive function signature. I guess one thing that I forgot is that we also include like the whole preceding contents of the file. So if we try to evaluate on the definitions in the middle of a file, we also include the first part of the file, or at least as much as fits into the context window. OK, and with that, we can look at how well this does. And the surprising thing is, so this chart shows us how well the 5 different models do on those 3 classes. So what we first see is that, as expected, simply typed definitions are much easier to solve, although nowhere near 100%. And like the dependently typed ones and the proofs, they are significantly harder and with a lower success rate. And what we are measuring here is like a pass attempt. If we do 10 independent attempts at solving, predicting the definition, this counts the number of problems where at least one of those predictions checks without an error. And the interesting thing, so OK, let me explain one more thing. So the first 2 bars, the blue one and the orange one, they are GPT. 3.5 and GPT-4. And the other bars are smaller models that we evaluated and then we fine-tuned. So the solid bars at the bottom are the off-the-shelf versions of those. That's Phi2, Orca2, and StarCoder. It's already a bit older, this evaluation. And then the non-solid one above, that's the results that we get via fine-tuning. And so the really impressive thing here is that if you fine-tune like small model, in this case like StarCoder, then we get a performance that is almost as good, even better in our case, than if you use a GPT-4 off the shelf. At, of course, much lower cost and much more accessible on your own machine. OK, and this is maybe another like just interesting diagram, is that we can actually like see what the models learn while fine-tuning. So what we see here on this chart is the distribution of errors when running the models. And so like the big blue thing is syntax errors. And what we see on like the models on the right is that this blue bar is almost everything. So like an unfine-tuned Phi2 or StarCoder, it makes a lot of syntax errors. Like what we've heard before, like missing parentheses and so on. But if we fine-tune it, then those syntax errors almost go away. And in a sense, what we see here is that the model during fine-tuning learns how to write syntactically correct code in our language that it wasn't part of its training set, where we have very little data. And the other important takeaway here is that retrieval augmentation is really, really important. Just adding this extra context to the prompt of, hey, this is a relevant definition, and hey, this is the previous content of the file. I mean, this helps enormously. So the first line in this table here shows us how good the model is with all our like augmentations applied. And like this is a phi2 model. It's small. If you try all these permutations, then you want to have a small model that you can fine tune quickly. So this is not the best one, but the one that we can train pretty quickly. And so like the first line shows how well it does with all of these optimizations applied, and there we get I don't know, like in the intra project column, like 31%. And if we, for example, drop the file content up above the current definition, then it drops to 21%. If we drop the related example, then it drops to 26%. So like just adding these related examples in the context helps enormously. OK, this is very much like initial work. We've submitted it. Well, so it's an article at this year's ICSI. It is also like an extended technical report available. And from here on, we have some ideas on how to take this further. We want to cut down on identifier errors using monitor decoding, using where you, during inference, force the model to only generate valid identifiers by modifying the generated probabilities for the next token. We are looking at evaluating repair. Right now this is just like one shot, and as we've seen in the talks before, taking into account error messages helps enormously. So that's something we want to look into. And right, and another thing that I think people here are doing really great is like removing assertions from programs and trying to infer them again. That's also something we want to look into. And like one more thing that we want to do is, so right now we're generating like these whole like definitions in one go. And what we see is that like the longer these definitions get, the harder they are for the models to predict. So what we want to do is try to find ways to split this up so that we can, I don't know, like generate like one statement at a time. This is unfortunately a bit harder because F-star doesn't really have this statement-like structure that Dafny has. Thank you so much. If you're interested, we have a Zulip chat and a website, and thank you.
I guess one thing that's really nice about this is that you're not restricting to single procedure or single file, unlike a lot of LLM works in Dafny or in Rust. Do you think the techniques that you use to do that would generalize to other verified, like to Dafny or
Yeah,
Rust and Verus?
Like, that's kind of the thing. We're not doing really anything F-star specific, except for trying to classify like those definitions. Everything else should apply pretty much the same way to Dafny, I think.
Another small question: the 50% success rate on simply typed functions, it's just that synthesizing some function of that type?
Yeah. There is no constraints on it, right? So we're trying to only generate a single definition, so we're not trying to generate any proofs after it. So this is really the success. Hey, can the model actually write down a function with that type?
But then, now the 50% looks like a failure. I mean, if I just give you a type, how hard can it be to just synthesize that? Why is it not 100%?
Also, the thing is that you're in the middle of a whole development. So, like, if you get like a definition that says I need to produce a foobar object, then you don't know. Is it a mk underscore foobar? Is it, you don't know what definitions you have. You actually need to find like the correct definitions to be able to construct it. So like, on a theoretical level, this should be as easy as, looking through a library and trying to put together functions. But in practice, it's really like you don't know what these functions are. You don't know how big the term is going to be.
Thanks.
So early on, you showed a list of the F-star projects you were pulling from.
Oh, sure.
I was just curious. You might hypothesize some of these are easy projects and some are hard projects. Do you actually have any data to show which ones the LLMs did good at?
I'm not sure if I have actually any data on that. At least not any data that is ready. I mean, I guess like typically you see some difficulty changes there. I'm not sure how representative they are. It might be that, I mean, like even like these more complicated projects have parts that are like like some support libraries, and I would imagine that like this is just quantifying like how much support libraries you have there.
All right.
I'll take this opportunity to ask my colleague about this really. So I'm just curious as to when you run the small models, augmented small models compared to, say, GPT-4, can you say something about the cost benefits?
Well, yeah, so I mean, I don't have the dollar numbers in my head, but like GPT-4o does cost you more money than like small models, that's for sure. And the other thing is that you can run those small models on your own machine or on your own hardware. Which frees you from like this whole accounting thing of who buys for the credits.
Okay. Thanks.
Well, let's thank Gabriel again.